Hello everyone and welcome back. In the previous lecture, we have discussed elaborately about the complete graph and the complement of a graph. We have seen how we can draw the complement of any given simple graph. Well, in today's lecture, we will be discussing these particular topics which I mentioned here on this slide. So, we will learn in details about clique and independent set in a graph. How can we determine the maximal and maximum cliques and independent sets? And in addition to these, we will also learn how to find out the clique number and the independence number of any given graph. So without any delay, let's start today's lecture, and the very first topic of discussion today is clique in a graph. So what do we mean by clique? Now, as per the definition, clique is a set of vertices in a graph which are pairwise adjacent to each other. So first of all, we have to make it clear that clique is a set of vertices. Many confuse it with graph. Clique is not a graph. Clique is a set of vertices in a graph. Now let us see with the help of an example what it actually means. So for that, let me draw a graph first. Let this be my graph G, where the vertices are labeled as U, V, W, X. Now in any graph, how to find out the cliques? So we need to find out sets of vertices which will be pairwise mutually adjacent to each other in the graph. Meaning, a set of vertices, let me just give you a rough example first. Suppose V1, V2, V3, V4, this is a set of vertices in a graph. Now, suppose this is a clique. Then what should it satisfy? Why is it called a clique? If this is a clique, that means for every pair of vertices that you can form from this set of vertices, that pair of vertices are adjacent in the given graph. So basically, from this set of vertices, what are the pairs that I can form? V1, V2, V1, V3, V1, V4, V2, V3, V2, V4 and V3, V4. These are all the pairs of vertices that I can form. Order doesn't matter. V1, V2 is a pair of vertex, means V2, V1 is the same pair of vertices. So these are all the pairs that can be created from this set of vertices. Now, this set is clique, means every pair of vertices that can be formed from this set, those pair of vertices are adjacent in the graph. That means in my graph, definitely the two vertices V1 and V2 are adjacent to each other. Similarly, V1 and V3 are also adjacent to each other. So is for V1 and V4 and for all the rest of the pairs also. So that is the reason we term it as a clique. So basically, clique is a set of vertices only of the graph. Now which type of vertices? Such type of vertices so that you pick any pair of vertices from that set, you will find they are adjacent in the graph, and this you must check for every pair of vertices that can be formed from that set. Even if you find one single pair of vertices in that set which are non-adjacent in the graph, that will be enough for me to conclude that the set is not a clique. So basically, for a set to be a clique, every pair of vertices that can be formed from that set must be adjacent vertices in the graph. Now let's come back to our given graph G. So if I want to list down the cliques in a graph, we will start with the cliques of size 2, because you need a pair of vertices to be adjacent in the graph. For that, a clique of size 2, when I say size of a clique, I actually mean the cardinality of the clique, because clique is a set only, so we have cardinality of a set, that means the number of elements present in the set. So size of clique means cardinality of clique, that means the number of vertices that are present in that clique. So if I talk about cliques of size 2, then you will find, for example, in this graph, U and V. These two vertices, if I put them in a set, now the only pair of vertices that can be formed from this set is the pair U and V. So U and V in the graph, I can see they are adjacent. So they satisfy the criteria of being a clique. That is why I term this a clique. This is a clique here. Okay. Similarly, if I see the set of vertices V and X, the only pair that is created is Vx and they are adjacent in the graph, so that is also a clique. Similarly, Vw is a clique, Xw is also a clique. So basically, you will find that in a graph, every single edge will have its end vertices participating in a clique of size 2. So as many edges you have in your graph, those many cliques of size 2 will be created. See, my graph is having 4 edges. Accordingly, 4 cliques of size 2 are created. Each clique of size 2 corresponds to the end vertices of each edge. Okay. Now when you have listed down all the cliques of size 2, now you move forward to find if there is any other clique of size 3 or more. Now if there is any clique of size 3 or more in the graph, those cliques will be formed only as an extension of these existing cliques of size 2. How? For that we need to check if we can extend any of these cliques of size 2 any further. For example, let's start with the clique of size 2 UV. Is it possible to extend this clique further to a size 3? Now for that I need a new entry, a new vertex has to be entered. Now when you have a clique and you want to extend that clique to a larger size, it is possible by the entry of a new vertex. Now not the entry of every vertex will make it a clique. So given a clique, the entry of a vertex is allowed in that clique only if the new entry is adjacent to each of the existing vertices in your set. So here I have the vertices UV. You have to check whether W or whether X can be included with U and V so that the resultant set of 3 vertices is also a clique or not. So think about it. If you want to insert W, can you? Now the new entry W, if it has to enter this set and be a clique, then W has to be adjacent with each one of the existing vertices U and V. Now we see W is adjacent to V in the graph, but W is not adjacent to U. So I cannot have this entry W in my set UV, because if I form this set UVW, see, this will not be a clique. Why? Because here I have a pair of vertices U and W which are non-adjacent in my graph. Now that dissatisfies the definition of being a clique, so this will not be a clique. Similarly, check whether UV can be extended further by the entry of the other vertex. Another vertex is there X. Can you make that vertex enter into this clique and still keep it a clique? No. Why no? Because the new entry X is non-adjacent to U, although it is adjacent to V. So UVX will not be a clique. So the clique UV basically cannot be extended any further by the entry of any of the remaining vertices W or X. So there is no clique of size 3 that can be formed from the clique UV. Next you have to check for Vx. So given V and X, can I extend this clique further? See, can I enter the vertex U here? If I enter the vertex U, U will be adjacent to V as it is in the graph, but U is not adjacent to X. So definitely V, X, U, these 3 together will not form a clique. What about W? Can I enter the vertex W in this set and still it will be a clique? So if I enter W, check. What are the pairs of vertices that are formed with this set of 3 vertices? Vx, Xw and Vw. Now in the graph I see each of these pairs of vertices are adjacent. See, V and X are adjacent, V and W are adjacent, W and X are also adjacent. So this is a set of vertices, this is a set of 3 vertices which are pairwise mutually adjacent to each other, and that makes it a clique. So we have our first clique of size 3, that is VXW. This is a clique. Next we move to the clique VW. Can I extend VW to any clique of larger size? Can I include U in this set? No, because U although adjacent to V, U is not adjacent to W. Can I include X? Yes, X is both adjacent to V and W in the graph, so I can extend this to form the set VWX, which is same as the clique already obtained here, VXW. So that doesn't give us any new clique, but we get the same clique again. Next we move to XW. So if we have this clique XW and I want a new entry, what I can enter here is V. If I enter V, I am again getting the same clique of size 3, and of course I cannot enter U because U is not adjacent to X and W, both of them. So basically as a clique of size 3 I am only getting VXW. Now can I get a clique of size 4? If you are to have any clique of size 4, then that will be formed by any of the cliques of size 3. Now here you have only one clique of size 3. So proceed further to check if this clique can be extended any further to a clique of size 4 or not. So if VXW has to be extended, then the only possible entry could be U. Can I enter U? U is adjacent to V but non-adjacent to X and W. So you cannot enter this clique and still be a clique. So I don't have any clique of size 4 here. So these 5 are the only cliques of my given graph G. So this is how we determine and we list down all the possible cliques in a graph. Let's see another example. Take a graph G. Suppose this is our graph and we name the vertices as A, B, C, D, E. Let us list down all the cliques in this graph. So we have AB. This is a clique because A and B are adjacent to each other in the graph. We have BC. We have AC, CD, CE and DE. See, the size of my graph is 6 and I have 6 cliques each of size 2. Now can I have a clique of larger size, that is of size 3? If we are going to have any clique of size 3, it will definitely be formed by some of these cliques of size 2 only. So we have the clique AB. Can we have a new entry in this clique? See, can I enter the element or the vertex C here? If I enter C, I have a set of 3 vertices. Now let's check if every pair of vertices here are adjacent. Now in my graph, AB are adjacent, BC are adjacent, AC are also adjacent. So all the pairs of vertices that can be formed from this set of 3 vertices ABC are adjacent in the graph. So that makes it a clique of size 3. Can we extend AB by the inclusion of D? No, because ABD will not be a clique because A and D are non-adjacent or B and D are non-adjacent. Similarly, A, B and E will also not form any clique. Now what about the clique BC? BC again can be extended by the entry of A and that will create the same clique ABC. Other than that, we cannot extend BC by the entry of either D or E. AC also similarly will create the same clique ABC by the entry of the vertex B. So it will be a clique of size 3, the same clique again. And AC cannot be extended further to include D or E because that will not be a clique. Now come to CD. Now when you have C and D, if I include A here, then A is adjacent to C but A is not adjacent to D. So C, D, A is not a clique. Similarly, B if entered, then B and C are adjacent but B and D are non-adjacent. So C, D, B will also not be a clique. But if I enter E here, I will see CD, DE and CE. Every pair is adjacent in my graph. So this is a clique of size 3. C and E, this also will be extended to form the same clique CDE and DE will also be extended to form the same clique CDE. Now check if you can have any clique of size 4. If you are to have any clique of size 4, that will be created by any of these cliques of size 3 only. Now ABC cannot be extended any further by including D or E because there will be non-adjacencies. Similarly, CDE also cannot be extended. So these are all the possible 8 cliques in this particular graph G. Now if you observe carefully, you will find the participating vertices in a clique actually form a complete graph on their own. For example, see A and B, this is a clique. In the graph A and B, these participating vertices of the clique are forming a complete graph K2. See ABC. In the graph, the vertices A, B and C are creating the complete graph K3. So basically the participating vertices of every clique, they form a complete graph on their own in the whole graph. So that is one way of determining whether the graph has a clique of size 3 or more, just looking into it. So that might be helpful sometimes. For example, in this graph we can clearly see there are 2 K3s in the graph. One is ABC, one is CDE. So if I am having K3, that is a complete graph of order 3, then definitely those vertices of K3 will participate in a clique, because a complete graph is defined in that manner that every pair of vertices in a complete graph are adjacent to each other. So let's see another example for that. The vertices are U, V, W, X, Y. Let us list down all the cliques. So we have U, V, V, W, W, X, X, Y and V, X. 5 edges are there, so 5 cliques of size 2. Now in the graph itself I can see there is a K3 in the graph which is created by the vertices V, X and W. So I am very clear that these vertices V, X and W will form a clique. See, Vx, Xw and Vw, all the possible pairs from this set are adjacent in my graph. So that is a clique of size 3. Now if you observe carefully, there are no other cliques in this graph. So these are the only 6 cliques of my graph G. Now the next particular topic is how to determine the maximal and maximum cliques in a graph. So whatever graphs we have discussed already, in relation to that only let me explain what I mean by maximal and maximum cliques. So in this graph we had cliques UV, VW, WX and Vx, and I have a clique of size 3 created by Vx and W. So these are all the cliques of my graph. Now what do I mean by maximal clique and maximum clique? So let me explain maximum clique first, because that is easier to understand. Maximum clique is the clique of the largest cardinality in the graph. So here there are 4 cliques of size 2 each and there is a clique of size 3. So which is the clique of the highest cardinality? This one, the clique of cardinality 3. So that is the maximum clique. So here maximum clique is Vxw. Whichever is the clique of the largest cardinality, you may have more than one also, those will be maximum cliques. Here we have only one. Now what about maximal cliques? So maximal cliques are those cliques which cannot be extended any further to a clique of larger size, or maximal clique is a clique which is not contained in any larger clique, or maximal clique is a clique which is not a subset of any larger clique. So basically a clique which has stopped extending, which has saturated, it cannot be extended any further by the entry of any new vertex, that particular clique will be called maximal clique. Now for that we need to list down all the cliques present in the graph, and then it will be very easy for us to choose all the maximal cliques from that list. So here we have already listed down all the cliques. Here we can see the clique UV, that is not extended any further because the extensions are all listed here. These are the cliques of size 2 and this is the only clique of size 3 that is extended from VW, WX, VX. These 3 cliques are extended basically to form this clique of size 3 VXW. Now UV, this clique has stopped extending, it is saturated. You cannot extend this clique any further to a clique of size 3 by an entry of any vertex, right? If it would have been listed here. So we don't have any clique of larger size that is created by UV. So UV is not contained in any larger clique, or it is not a subset of any larger clique. That makes it a maximal clique. Okay, now come to VW. See, VW, this clique is a subset of this larger clique VXW, because VW, these vertices are contained in this clique VXW. So VW is extended further by an entry. That does not make VW maximal. So VW is not maximal, and for the similar reason WX, VX, they are also not maximal because they are all extended further to a clique of larger size. That is the reason UV is maximal, because it has stopped extending. And what about the maximum clique VXW? See, VXW is also a clique which has stopped extending any further. It is not contained in any larger clique because there is no clique of size 4 in this graph. So that clique itself is also maximal. So you will find every maximum clique is definitely maximal clique. but all the maximal clicks need not be maximum clicks. Okay, so in short, maximum clique is the clique of the largest cardinality, and maximal clique, they can include cliques of different sizes. You have to only search for those cliques which are not contained in any larger clique. So let's see another example. The vertices are A, B, C, D, E. Okay, so all the cliques here are A, B, B, C, A, C, C, D, D, E, and C, E. And cliques of size 3, we have 2, A, B, C, and C, D, E. These are all the cliques of this graph. So we have 2 maximum cliques here, A, B, C, and also C, D, E, because both are cliques of the largest cardinality, that is 3. And what about maximal cliques? Let's see. AB extended to form ABC, BC extended further to form ABC, AC extended to form ABC. So each of these 3, none is maximal. Okay, they are all contained in this larger clique. CD, DE, CE, again these 3, each one of them is contained or is a subset of this larger clique. So none of the cliques of size 2 is a maximal clique here. Now what about the cliques of size 3? They are maximum cliques, so definitely they are maximal also. Every maximum clique is maximal clique also, because they have stopped extending, they are not contained in any larger clique. So these are the maximum here, these are the maximal also here. Let's see the other graph. So we have U, V, W, X, Y. Let us list down the cliques. U, V, V, W, V, X, W, X, and X, Y. These are the cliques of size 2, and I have a clique of size 3, V, W, X. Okay. So clearly maximum clique is the clique of the largest cardinality, that is V, W, X. And what is maximal clique, or what are maximal cliques here? Let's see. UV, see, UV is not extended any further, UV is not contained in our extended cliques, so UV is maximal. VW is extended here, VX is also a subset of this larger clique, WX is also contained in this larger clique. What about XY? XY is not contained in any clique of larger size, so that is also maximal. Is there any other maximal clique? Yes, the maximum itself is maximal again. Okay, so don't forget to include the maximum clique when you are calculating or when you are listing down the maximal cliques. So we come to the definition here. A clique in a graph G is called maximal if it cannot be extended any further to a clique of higher cardinality. That is, it is not contained or it is not a subset of any larger clique in the graph. And what is maximum clique? It is the clique of having the maximum cardinality in the graph. Next topic is clique number. So the definition goes like this. Clique number is defined as the cardinality of the maximum clique in a graph and is denoted by omega g. So whatever we have discussed until now, clique number is determined from the size of the maximum clique. So to know the clique number, we have to find out the maximum clique in the graph. Its cardinality is the clique number. So clique number is a number which is the size or the cardinality of the largest clique in the graph. So if we see the same graphs, I'll just mention the clique number for each graph. If you remember, in this graph, the maximum clique was VWX and the cardinality is 3. So the clique number, which is denoted by omega, then the name of the graph within bracket, omega g, the clique number is 3, which is the cardinality or size of the maximum clique. Then we have this graph. Here also the maximum clique was a clique of size 3, so its clique number is also 3. And lastly, we have discussed this graph. Here also we have a clique of size 3 which was maximum, so omega g is 3. That is how we determine the clique number of a graph. Let's take a very simple graph. Labelings are P, Q, R. So what are the cliques here? P, Q, P, R. We don't have any other clique in this graph. So here these are the maximum cliques, the cliques of the largest cardinality, and they are only the maximal cliques also. And here omega g, or the clique number, will be the size of the maximum clique, that is 2. So here we have that graph on this slide. PQ and PR are the two cliques. A clique of size larger than 2 does not exist. That is the reason omega g, or the clique number, is 2. Maximal cliques are also these two, and they are same as the maximum cliques. Now we have another graph here where we can see the all possible cliques are UV, UI, UX, XY, XW and VW, each corresponding to the n vertices of each edge in the graph. And as we can see, there is a K3 in this graph that indicates there is a clique of size 3 created by XYU or UXY. So the maximum clique is UXY, the clique of the largest size, and that will only determine the clique number omega g. Now what about the maximal cliques? UV is not extended any further, or it is not contained in any larger clique, that makes UV maximal. UY is extended further to include X, UXY is the larger clique, so it is not maximal. UX again is not maximal because it is extended further, XY is not maximal. XW is maximal because it is not extended any further, so we have XW as maximal clique. VW is also maximal as it is not extended any further, so that is another maximal clique. So these are the maximal cliques of size 2, and of course the maximum clique is itself a maximal clique, that is of size 3. The clique number is indicated by the size of the maximum clique only. Next important topic is independent set in a graph. Independent set is defined as the set of pairwise non-adjacent vertices in a graph. Clique means set of pairwise adjacent vertices. Independent set is just the opposite, set of pairwise non-adjacent vertices. In clique we used to search for vertices so that every pair we can pick are adjacent in the graph. So in independent set we will search just for the opposite. We will make set of vertices in which every pair will be non-adjacent in the graph. That will be our independent set, or we can also term it as stable set. So let's see some examples. Suppose we have a graph G, vertices are A, B, C, D, E. So what are the independent sets here? Now you have to keep in mind when you are listing down the independent sets, the first independent sets are the singleton sets, that is the set containing only A, only B, the set containing only C. So all the singletons that can be created by the vertices themselves, they are all independent sets. Why? If I take the singleton, then I can't form any pair of vertices here. I have only the single vertex A, and that vertex A is not adjacent to itself in the graph. That is the reason we put singletons as independent sets. In the case if the graph does not have any loops, we are all dealing with loopless graphs here. So the absence of any loop at a vertex indicates that vertex is non-adjacent to itself. There is no loop, so the vertex is not adjacent to itself. That is the reason the singleton set A is an independent set, but the singleton set containing a vertex is not a clique, because to be a clique the vertices have to be adjacent to each other. So if we are talking about loopless graphs, you don't have a loop at a vertex, then the vertex cannot be adjacent to itself. So singleton set is not a clique, but singletons are independent sets. So you have to consider those first. After that, go to search for other independent sets of larger size. So can I extend A to an independent set of larger size? Yes. A can include C. Why? Because in the set AC, the pair of vertices A and C in the graph are non-adjacent. So here we are searching for non-adjacency. So whenever pairs of vertices are non-adjacent mutually, we can put them in an independent set. So AC is independent set. Similarly, from A I can also extend it further to include D. AD is independent set. Can I write AB as an independent set? Answer is no, because A and B are adjacent in the graph, but we are searching for non-adjacencies when we are dealing with independent sets. So A can be extended to AC or AD. Now what about B? B can be extended to include D only. B is adjacent to A, C and E, all of them. B is non-adjacent to D only. So B and D can form an independent set of size 2. Next we come to C. So C can be extended to include A. Now C and A already that's taken here as AC. C can include E also because C and E are non-adjacent. Then we come to D. D is non-adjacent with B and BD is already taken here. D is non-adjacent to A, so that is also taken here AD. Next we come to E. E is non-adjacent to C only and that is already taken here as CE. So these are all the independent sets of size 2. Do I have an independent set of size 3? So check if any of these independent sets of size 2 can be increased or not to an independent set of larger size. So AC, this set cannot be extended any further because there is no vertex in the graph which is non-adjacent to both A and C. Similarly, AD can also not be extended any further because there is no vertex in the graph which is non-adjacent to both of them. BD also cannot be extended any further because I cannot include A here with BD because A is adjacent to B. Similarly, BD and CE, they also cannot be extended any further, keeping the set as independent set. So these are all the independent sets that we can have in this graph G. It's just similar to cliques. The only thing that we have to think of is during clique all the focus should be on adjacencies, during independent set all the focus should be on non-adjacencies. Let's see another graph. Let's see one of those graphs that we have already dealt with. So this was one graph, suppose U, V, W, X, Y. Okay, so what are the independent sets? So we have to start with all the singletons. So U, V, W, X and Y. Next, U can be extended further to include X. It can also be extended further to include Y because these are the pairs which are non-adjacent in the graph. V can be extended to include X and also V with Y. Next, W. Now W in the graph I can see is adjacent to all the other 4 vertices. W is adjacent to U, V, X and Y. So there is no vertex with which W is non-adjacent. So W is not extended any further. And what about X? X can include V, that is Vx taken. X can include U, that is also taken. Similarly, Y can be extended further to include U, Yu taken, and it can be extended to include V also. Vy is also taken. Now is there any independent set of size 3? So let's see if Ux can be extended any further. If U and X have to be extended further, then we need a vertex in the graph which is non-adjacent to both of them. Now there is no such vertex. So Ux cannot be extended. Similarly, if you observe carefully, you will find none of these independent sets of size 2 can be extended any further. So these are all the independent sets in this graph. Let's see another example. Let us name them U, V, W, X, Y, Z. Okay, so what are the independent sets here? First we have all the singletons. Let me write it here. U, V, W, X, Y, Z. Now what are the independent sets of size 2? So as I can see, U is adjacent to V, W, X, Y and Z. So U cannot be extended any further because it does not maintain non-adjacency with any of them. Similar thing goes with Z also. Now let's see if any of these V, W, X and Y can be extended. Now V is non-adjacent to X, so Vx can form an independent set. V with Y also can form an independent set. Next we can see W with Y can form an independent set, and there is no other independent set of size 2. What about independent set of size 3? Now if we see carefully, we will find none of these independent sets of size 2 can be extended any further. So these are all the independent sets we have in this particular graph. Next, again the concept of maximal and maximum independent set. Concept and the idea goes same as cliques. So maximum independent set means the independent set of the maximum size in the graph, and maximal independent sets are all those independent sets which have saturated or which are not extended any further, which are not contained in any larger independent set, or which are not a subset of any larger independent set. Let's see with the examples. Suppose this is the graph, simple one, P, Q, R. So here the independent sets are P, Q are the singletons, then we have size 2 QR. No other independent set is there. So our foremost job would be to list down all the independent sets, then search for maximal and maximum. So here maximum independent set, let me write IS for independent set, it is QR, the independent set of maximum size. And what about maximal independent sets? See, P is not contained in any larger independent set, so that is maximal. Q and R are extended further to form QR. So none of these two are maximal. Next, the maximum itself is maximal. So these are the maximal independent sets. Let's see another example. So that was the graph we have discussed right now, U, V, W, X, Y, Z. So the independent sets are U, V, W, X, Y, Z. Then we have Vx, Vy and Wy. These are all the independent sets, of which maximum independent sets are those with the largest cardinality here, that is Vx, Vy and Wy. And maximal independent sets are those which have saturated. U is not extended any further, so U is maximal. V is extended, W is extended, X is extended, Y is extended, Z is again not extended, so Z is maximal. And all the maximum are definitely the maximal. Okay, let's see another example. See, this is K3. So if you list down the independent sets, you have the singletons A, B and C. There are no independent set of size 2 or more here. So these are the maximum and they are only the maximal independent sets also. So these are the definitions of maximal and maximum independent sets, similar way as we have defined for clique also. Next, independence number. Just like clique number, what is independence number? It is the size of the maximum independent set in a graph. So this is the definition as it goes. Independence number is the cardinality of the maximum independent set in a graph, and the notation that we use for independence number is alpha G. So if we see any graph, let's see for this graph U, V, W, X. Here if we list down all the independent sets, we will get singleton U, V, W and X. And of size 2 we have XV, out of which the maximum independent set is the set XV, whose cardinality is 2, so alpha G is 2. Let's see another example. Suppose this graph A, B, C, D, E. Here if we list down all the independent sets, we have singletons A, B, C, D and E, and those independent sets of size 2 are AC, AD, EC, EB and we have AE. There is an independent set of size 3 also, ACE. So the maximum independent set is the one with the largest cardinality, ACE. So the independence number is 3. Well, so let's see the problem presented on this slide. Here we have the graph with 3 vertices P, Q and R. We can see the singletons P, Q and R, they are the independent sets. Then we have only one independent set of size 2, that is formed by Q and R. Of these, the one with the maximum cardinality is QR, so that is the maximum independent set. And which are the maximal? As we can see, P is not contained in any larger independent set, so P is maximal. Q is extended further to create QR. R is also contained in the larger independent set QR, so they are not maximal. And QR being maximum is also the maximal. So we have 2 maximal independent sets. Now the maximum independent set determines the alpha G, that is the independence number. So here it is 2, the cardinality of the maximum independent set. Next we move to this example. So here we have 6 singleton sets as independent sets. After that we have V and Y as an independent set because they are non-adjacent. Similarly, Wy and Vx are also independent sets. So if we observe carefully, we will find there is no independent set of size 3 or more. So the maximum independent sets are those with the maximum cardinality, that is 2, and that makes alpha G, that is the independence number 2 as well. The maximal independent sets are all those independent sets which are not contained in any larger independent set. So in that sense, U is maximal because U is not extended further to any larger independent set. V can be extended, W can be extended, X can be extended, Y also can be extended. Z again cannot be extended, or Z is not a subset of any larger independent set, so Z is also maximal. Then all the maximum independent sets, they are also the maximal. So we have 5 maximal independent sets. Just remember, the independence number is determined by the cardinality of the maximum independent set. Let's see an example and we will discuss all the things that we have studied about cliques and about independent sets in this particular graph. Let us take a graph which is very known to us, K4. That is the complete graph of order 4. The vertices are A, B, C, D. Now let us list down the cliques first. So what are the cliques here? First we have all the cliques of size 2, that is AB, AC, AD. Then we have BC, BD, and we have CD. There are 6 edges, so the end vertices of every edge will provide us with a clique of size 2. Next we have a clique of size 3, ABC. We have a clique of size 3 again as ABD. We have ACD and also BCD. And lastly we have a clique of size 4, that is ABCD. Why? Because whenever we are dealing with a complete graph, we know it is a graph in which every pair of vertices are adjacent. So all the vertices taken together will definitely form a clique because every pair you pick, they are adjacent in the graph. That is why it is a complete graph. So here you have a clique of size 4 as well. Now what is the maximum clique? This ABCD is the maximum clique which is of the largest cardinality. That makes omega of K4 as 4. That is the cardinality of the maximum clique. And which are the maximal cliques? If you see, all of these cliques are extended further to cliques of size 3. All of these cliques are extended further to create this clique of size 4. So the clique of size 4, that is ABCD, that is all the vertices of the graph taken together, is the only maximal clique. All other cliques have been extended to create this maximum clique. So there is only one maximal clique, that is the maximum clique itself, ABCD. Now let us list down all the independent sets. So we have, so this is all about clique in this graph. Let us now deal with independent set. So we have all the singletons A, B, C and D. Since all the pairs of vertices here are adjacent, so there is no pair of vertices in this graph which are non-adjacent. So we are not going to have any independent set of any size greater or equal to 2. So these are the only independent sets, so they will be our maximum, they will be our maximal as well, and that will indicate alpha K4, that is the independence number, is 1. Now let's go through this particular example. Here we have cliques of size 2 indicated by the end vertices of every edge in the graph. Then we have cliques of size 3, as we can see 2 K3s in this graph. One is U, V, Y, they are forming, another K3 is formed by V, Y, W. So these are the 2 cliques of size 3. And there is no other clique of size 4 or more because there is no K4 in this graph. So that indicates the maximum clique is of size 3. They are these 2, and accordingly the clique number is 3, and the maximal cliques are WX, UVY and VWY. If you observe carefully, you will get this result. And on the same graph, we have listed down all the results regarding independent sets as well. So here we have the maximum independent set of size 3 only, that indicates the independence number is 3. These are the maximal independent sets which are listed over here. So you can work out this problem on your own and check how these results have arrived. Now there are some key points to remember in relation to clique and independent sets. Let us take an example of a graph. Suppose this graph, we have already dealt with this in this lecture. Now let me draw the complement of the graph G. Now this is something related to the previous lecture. So we will have the same 4 vertices as in our graph G, and I'll place them in the same locations. So we have U, V, W and X, and we will draw those edges in G complement which are not present in G. So we search for all the non-adjacent vertices in G and make them adjacent in G complement. So accordingly, U is already adjacent to all the remaining vertices. So in complement, U will not be adjacent to any of the vertices. In G, V is not adjacent to X, so we make V adjacent to X in G complement. In G, W is adjacent to U and V but not to X. So in complement, W will be adjacent to X. X was not adjacent to V and W. So in complement, see, X is already being made adjacent to V and W. So we are done with the complement of the graph. See, we have 4 vertices. So together they will form K4. Now K4 has number of edges 6. In the graph, we already have 4 edges. So 6 minus 4, 2 edges should be present in the complement, and we have already drawn the correct 2 edges. So this is G complement. Well, so what I need to mention here is that suppose in graph G we are having a clique, XU is a clique. In the complement you will see X and U is an independent set. See, U and X are non-adjacent in G complement, so that is an independent set. You will see U, V, W is a clique in the graph G, and the same set U, V, W is an independent set in the complement because every pair in this set are non-adjacent vertices. Again, X and V, they form an independent set in G, and that set X and V forms a clique in the complement. So basically the point is, every clique in the graph is an independent set in the complement of the graph, and every independent set of a graph is a clique in the complement of that particular graph. Now here is one exception when we talk about the singleton independent sets. Now the singleton independent sets in the graph G, they do not form cliques in the complement. Except for those, any clique in the graph, you will find it as an independent set in the complement. Any independent set other than the singleton will be a clique in the complement. So in a similar manner, if we calculate omega G, we will find here the clique number is 3 and alpha G, the independence number is 2. And if we see, the clique number of G complement is 2 and the independence number of G complement is 3. So basically the clique number of a graph is the same as the independence number of the complement of the graph, and the independence number of a graph is same as the clique number of the complement of the graph. So these are some key points that we should remember. They are listed over here. A clique in a graph G is an independent set in G complement. Similarly, an independent set in a graph G is a clique in G complement. Now here we don't take into account the singleton independent sets when we are pointing this out. And the clique number of a graph is the same as the independence number of the complement, and likewise the independence number of the graph is same as the clique number of the complement. Well, so that's all for today. I really hope that you are finding these lectures helpful. Still, if you have any queries or suggestions, please do write in the comment section below and let us know. Till then, thanks for watching. Take care and bye-bye.